power 6 is equal to 1. And z to the power 8 is equal to 1. Let's try to solve these two systems, or these two polynomials. So if we have two polynomials, we expect to get here, here we expect 6 different roots, here we expect 8 different roots. The ones that might be obvious, at least in the real number space, so if we consider the real number space, here we might get 1 and minus 1. And that's it. And similarly, in the real number space, we might assume that these two are a pair of numbers which are accepted as roots. But here we need 6, here we need 8. How can we do that? Here we can use a notation which can help us, which is going to be, so not here. So let's have a look at how we denote I. So I, this is equal to e to the power I times 90 degrees, okay? Because this is equal to cosine 90 plus I sine 90. Cosine 90 is equal to 0, so we know this one. This is equal to 0 plus I times 1, which means that it is I. So we prove this one also looking at the Euler identity. Now this is I, because this is 1, and this is minus 1, and minus 1 is equal to e to the power I times 180 degrees. Okay? Why is it so? Because to go to I, we rotate by an angle of 90. To go to minus 1, we rotate another angle of 90, so we get 180. And we can check whether this is true by checking the following. This is equal to cosine 180 plus I sine 180. Cosine 180 is equal to what? This is minus 1, and sine 180 is 0. So we get here minus 1 plus 0 times I, which is minus 1. Now, similarly, we can see what is minus I. Minus I, it is equal to e to the power I to the angle minus 90, because we move by an angle of 90 degrees down to here. Again, we can check whether this is true. This is going to be cosine 90 plus I sine, minus 90. And this is also a minus. And similarly, we still get the minus I. Now, let's come, but then the question is this: what is 1? How can we denote 1 using the polar representation? So we want to describe 1 as r to the power I theta. Now, the magnitude of 1, it is equal to 1. So also here, the modulus of I is 1, modulus of minus 1 is also 1. So here it's going to be 1. So this one, it can be equal to e to the power I times 2 pi. Okay? Well, because 1 is right here. So then, if we rotate here by an angle of 2 pi, we still get 1, right? And then, if we rotate by another 2 pi, we get 4 pi, we still get 1. So it looks like if we multiply here by n, where n is an integer, we can always get 1. So 1 in polar notation, this is what it is. Or polar representation, where n is equal to 0, 1, 2, and so on. Okay. So then, if we're looking for the respective roots in here, we can write this one as e, or let's write it like this: exponential of I times 2 pi times m. And similarly, this can be equal to exponential of I times 2 pi times m. So then, if this is z to the power 6, we say that z is equal to the power 6 all to the power 1 over 6. Okay, so there is nothing wrong here. but then this would be exponential of e times 2 pi times n divided by 6. And similarly here, we have z is equal to z to the power 8, all to the power 1 over 8 times exponential of I times 2 pi times n divided by 8. Now, this is the time where we need the board back. So we are looking for roots that have a distance of 1 or modulus 1. Let's call this one modulus 1. And the roots, they're going to be somewhere around here, somewhere in this circle. But where are they exactly? Let's see what we get when n is equal to 0. When n is equal to 0, what do we obtain here? We find that z1 would be equal to exponential of I times pi over 3. Okay, so we simplify, we cancel out, we simplify by a factor of 2. Then here we have times 0. What is e to the power 0? Alisa?
1.
That's true, it's 1. So 1 root is right here. This is 1. And then let's check what is for the next n. Z2, this would be equal to the exponential of I times pi over 3 times 1. What is this value? Alisa, can you find this?
Isn't it I?
No. Let's see what it is. In fact, before substituting the values, you should be able to find that this is a rotation by pi over 3. It's equal to 60 degrees, right? So pi over 3, it is equal to 60 degrees because it's equal to 180 degrees divided by 3, right? So this exponential here, using the identity, which I can write here at the top, e to the power I theta is equal to cosine theta plus I sine theta. Boshti cosinuseve është boshti horizontal. Boshti sinuseve është boshti vertikal, okay? Prandaj boshti cosinuseve çfarë do kemi me këtu? Do të kemi this, what is the exponential of I to the power 3? This is equal to cosine 60 plus I sine 60. Okay? What is the cosine 60? It's 1 over 2. So it's 1 over 2 here. So then we get this value. Okay? So this is Z2. Now for n equal to 2, Z3 is equal to the exponential of pi over 3 times 2. What is this? Where can we find this value? So this value we can find if we rotate by another 60 degrees. So we get right here. Okay? So this is pi over 3. This is e to the power I, 120. n equal to 3, we get Z4 is equal to e to the I times 180. So we get this value. This is also another root. n equal to 4, we get Z5 e to the power I plus another 60, we get 240. The angle by 240, we get somewhere here. Then we get Z6, it's e to the power I times 300. 300 is 30 degrees after the 270. This is not very precise, sorry. more like here. Then the final value, Z7, is equal to e to the power 360. What is e to the power 360? This means that we are rotating by 2 pi, so we go back to the initial value. So here we have all the 6 roots of this polynomial. So the roots are 1, 2, 3, 4, 5, 6. That's how many we need. Now, this term here, this would be equal to e to the power I times pi over 4 times n. Okay? Or we can also write this one, e to the power I times 45 times n. Now so let's search for these roots. We first set n equal to 0. If we set n equal to 0, the first value we obtain is this one. Okay, so which is e to the power I times 45 times 0. E to the power I 0, this is 1. N equal to 1, e to the power I, 45 times 1. So we rotate by an angle of 45, so we get this value here. So which is separating this plane like this. So we have another root right here, which I'm trying to show it in red. N equal to 2, this is e to the power I, 45 times 2. What is 45 times 2? It's going to be the angle 90. So we're going to get another root right here. N equal to 3, we get e to the power 45 times 3, e to the power I, 135. So we get this value, and it is obvious that we are going to find another root each time we rotate by an angle of 45. So we get here, this is another root, here is another root, here another root, here another root, and finally we get this. So how many roots did we find which are shown in red? We get 8. That's 1, that's 2, that's 3, 4, 5, 6, 7, and 8. Okay. So these are, the first one is a little exaggerated, but that's fine. So it looks like we could find 6 different roots for the first polynomial and 8 different roots for the second polynomial. So this is like the nth root of 1.